Hello everybody, welcome to video 7 of STA 513. We'll go to the screen share and we'll begin from where we left off with video 6. So video 6, we left off right at slide 56, where now we want to do basically what we did in the previous chapter, chapter 17, where we start defining linear contrast. Now, the linear contrast can either be in terms of the main effects. In this case, this is giving us the formula of the linear contrast as a function of the level i's of factor A. So some linear combination of that. Or similarly as a function of the levels of factor B, as we see the j's go on. Now, the big thing with the standard errors, or in this case, this is the variance of the contrast, is that it depends on MSE times the sum of the coefficients squared over n, but B ends up being the number of levels of factor B in the first case, and the number of levels of factor A in the second case. Now, obviously, we're not deriving this by hand. We're letting SAS do the work for us, or again, like I said before, whatever software you're using will do the derivations for us. But the big thing is it depends on the MSE, the coefficient squared, and that becomes the component of the linear contrast. Now, these linear contrasts of the main effects are fine and all, but I really think we want to get involved in the linear contrast of the cells, of the cell means. Now, the big thing with all this is, when we start getting into the multiple comparisons, we start always get into that inflated alpha issue. And we saw the previous video, we could actually get after this by looking at the multiple comparisons in the LS mean statement, doing the adjust equal Tukey, the adjust equal Chaffee, or the adjust equal Bonferroni. So again, if we go back to SAS, one of the things we left off at is line 308 or 307, 308, 309. They're the three adjustment techniques. Again, there's a couple variations of this, but these are the three most common. And as I said previously in the one-way ANOVA model, is you really need to get involved with your data analysis management plan, statistical analysis procedure, statistical operating procedures, whatever it's called. DAMP for the first one, SAP for the second one, SOP for the third one, and really see what they recommend as the adjustment technique. And the big thing with these adjustment techniques is that the pairwise comparisons that you're talking about, in this case, the height by width, all the pairwise comparisons of those cells, the whole collection have an overall alpha of 0.05. So that's really the big thing of getting after that. In this case, in line 279, now we got the LS means for the main effect of height, weight, and the interaction. Now, when we say adjust equal Chaffee, that means the pairwise comparisons of height. Remember, there's three heights. So those three choose two, three pairwise comparisons. The overall alpha for at least one of them making a type 1 error is 0.05. That's controlled for this. The width, there's only two levels, only one pairwise comparison. That has an overall alpha of 0.05. And then the interaction for the 6, choose 2, 15 pairwise comparisons. The overall alpha for any one of them having at least type 1 error is 0.05 under the Chaffee adjustment. Now, the adjust equal Chaffee does each of the individual terms multiple comparisons, or we call family comparisons, being 0.05, not all three of them. So just be aware of that. It's just really the effect within the term, the two-way term or the main effect terms, as we saw before. But again, this is the easiest way, I think, in the LS mean statement lines 307, 308, 309, to do the recommended pairwise comparisons that you may be interested in. Pretty simple. Again, if we go back to the output for these three techniques, right? So right here, so adjustment for the multiple comparisons, for the 6 comparisons, or for the 6 cell means, and in this case, the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 6 choose 2 pairwise comparisons. So those 6 choose 2 pairwise comparisons have an overall alpha, or the family level alpha, of 0.05 in this scenario here. So again, these confidence intervals, that simultaneous multiple comparison, has an overall alpha of 0.05 for at least one of them having a type 1 error, which is really what we want to do. Is, well, actually in this case, control for all of them, the total composite having a 0.05 alpha level. We saw before the adjustment techniques made the unadjusted confidence intervals wider to protect against that issue of making a false type 1 error. And again, it does pretty good. Here's the Bonferroni output. So let's keep an eye on a couple of them. So let's look at the 5-6 comparison. So the 5-6 is comparing, in this case here, well, we'll do the 4-5 comparison rather. So the 4-5 is height 2, width 2. So it's the middle display wide shelf has 69 cases on average, and the top regular has 40. So 4-5, so it's an on average difference of 29. 69 minus 40. So when we go to the 5, my fault, we go to the 4-6 comparison, my fault, the 4-5 comparison, we can see that's still highly significant even under the Chaffee adjustment. So the 4-5 confidence interval with the Chaffee is 13.94 to 44.06 if we round it to 2 decimals. So the 4-5 comparison under the Bonferroni, if we check this out, so the 4-5 gives us this confidence interval, which is 13.90 if I round it to 2 decimals, 44.10. And then when we go to the, that was the Bonferroni that we had there, that was the Chaffee. Did we ask for the Tukey? Let's go ahead and slide up. It looks like we did. And this one is the Tukey. So the 4-5 comparison is 16.21 to 41.79. So now in this example here, in this example here, we saw the pairwise comparisons can be done with the LS means command. Here, we end up seeing the Tukey, so the 4 versus 5, which again, I think is middle wide versus top regular. We see the confidence intervals under the Tukey ended up being 16.21 to 41.79. We saw that the Chaffee ended up being 13.94 to 44.06. And then the Bonferroni, right, if we make these all look kind of comparable to their width. Whoop. And then the Bonferroni gave us just a hair wider as compared to the other two. So in this case here, doing the pairwise comparisons for the 2A ANOVA, the Tukey gave us the most narrow confidence intervals. The Schwey was next, and then the Bonferroni gave us the widest. So again, in this issue, if we were trying to find the best confidence intervals, it's really the ones with the smallest width that we feel are the best as trying to capture the true average contrast without, being overkill that we see a lot of times. The Bonferroni ends up being at overkill. Well, so far we've seen in estimating cell means you could do it either via the mean statement or the Ellis mean statement. I usually lean on the Ellis mean statements. And really the big thing with the mean statement is the means are not adjusted for other effects in the model. When we have the ANOVA, it's truly estimating the cell means. But for one way without any covariates, it's okay. But the Ellis mean statements are adjusted for effects in the model. And the biggest effects we want to worry about later on are what we call covariates. So they end up being the covariates as we move on. So things we want to adjust for. So the estimators of the means, the Ellis means are really estimators of the means that we would have expected if the design was balanced on average. The Ellis means are basically adjusted means. The means are basically observed means. So really the Ellis means, especially when we bulk up the models to include covariates or confounders, they're really what we want, those adjusted means as we move on. So again, we get estimate the cell means, for each of the interactions. The cell means are some of the data within the cell. So the sum of, actually the mean of the data is within the cell. And then the variance of that ends up being a function of the MSE divided by the cell size. And then there's the T linked to it. Now we can form contrast of these cell means, which is what we want to do next. Now the contrast are estimated by the respective sum of the cell means with the respective coefficients, the CIs, and then the variance of the contrast, MSE over N times the sum. Now we have a double sum because we have two factors, where we sum over factor A and factor B. So the sum of the coefficients squared. So this becomes our contrast of interest. So if we go back to our program on chapter 19, we can see here, as we start moving on, here I start estimating the cell means. The cell means. Before we get that, I'm going to just put the quit here and run the output again. So when we start running the output again, pay attention to the output, right? Couple things before. The class statement, it determines the order of the factors in the model. Not so much the model statements, really how they're laid out in the class. So class, height first, width second. So when we're creating a model formation, line 323 is telling us as we go across the iteration of the cell, it's basically identifying the I and the J. The I is height, the J is width. So when we start doing cell means, the J iterates in the I, right? So the width iterates per level of height as we start moving on. So if we go here to the output, So as you see here, in the order, it's first the height, then the width. Then if you look at the interaction term, we have the width iterating within each level of height. So height, width, 1, 1, 1, 2. Height goes to 2, width to 1, 2, 2. Height goes to 3, width 1, 3, 2. So we got the width iterating in the height as we start moving forward with respect to what we got going on. So when we start building the cell means, so again, anytime we want to make a contrast, the cell means are really important as we start moving forward with respect to trying to create these cell means. Right, so when we go here, we'll just take out part of this output. So again, we'll run this really quick. Right, so the big thing is this statement here, which identifies the class statement. Whoops, didn't want to do all that. So we'll go back to our notes. And then we'll go back to the output real quick, if I can get to it real quick, and then the parameterization of the model. So the class statement is telling us, okay, this is factor A, this is factor B. So in any kind of parameterization, factor B iterates within factor A. So in our parameterization, we get the intercept, which is the reference cell. We get the levels of height, with the last level being served as the reference group. We got the width, last level of the reference group. And then we got the height by width interaction. Like we said, you know, this indicates the level of height. The last one indicates the level of width. So 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, 3, 2. So again, that determines the parameterization of the model. So like we did in one way, if we want to estimate the cell means, again, we could do it manually. Now, remember, we said the idea of estimating the cell means, it allows us to create whatever contrast we need by taking the cell mean and adding coordinate-wise. So exactly what we saw in chapter 17 that we're doing real quick here. So if we go to mu1, 1, so we need the intercept, 1. We need the height, level 1. We need the width, level 1. And then the height, star width. So again, remember, we have the width iterating within the height. So the first one's height 1, width 1. Height 1, width 2. Height 2, width 1. Height 2, width 2. Height 3, width 1. Height 3, width 2. That's the first cell. Again, we're going to do all these manually. So mu, height 1, width 2. So I got the width iterating in the height. So again, we go here, intercept 1. We're at level 1 of height. Width, we're at level 2, not level 1, level 2. And then for the height by width interaction, remember this is height 1, width 1, height 1, width 2. Height 2, width 1, height 2, width 2, height 3, width 1, height 3, width 2. Then we do the same thing, mu2, 1. So we got the intercept and getting the cell mean. height, we're at level 2. That's level 2. Width, we're at level 1. Then the height, star width, interaction, we go height 1 with 1. Height 1 with 2. Height 2 with 1. Height 2 with 2. Height 3 with 1. Height 3 with 2. So again, we got the widths iterating within the heights. So we'll do the same thing for the 2, 2 cell. Intercept. So we go 1. We go height, level 2. Width, level 2. And then for the height by width interaction, go height 1 with 1, height 1 with 2. Height 2 with 1, height 2 with 2. Height 3 with 1, height 3 with 2. Then we do the same thing for the last 3 cells. So mu 3, 1. Height, level 3. Width, level 1. Then height, star width. So again, we do it again. So height 1 with 1. Height 1 with 2. Height 2 with 1. Height 2 with 2. Height 3 with 1. Height 3 with 2. So again, the 0, 1s are on-off switches, and we're turning them on when we're at the correct respective cell. So the 3, 2. Height, level 3. Width, level 2. And then the height, star width. So height 1 with 1, height 1 with 2, height 2 with 1, height 2 with 2, height 3 with 1, height 3 with 2. So there are 6 cells. And again, if you remember what we did last time, the 6 cell means are 45, 43, 65, 69, 40, and 44. So if we go to our estimate statements and see if we get the same thing as we start going here. So with the estimate statements right here, we got 45, 43, 65, 69, 40 up. Something went on with mu 3, 2. So up, that didn't pop out. Let's see if the log said anything to us. So the log said mu 3, 2 is not S1. That means something's wrong with the statement. And if you guys saw with the syntax, what is wrong with the statement is I had the 0, 1 together. When I put the space between them, that one becomes correctly estimable. So again, our cell means were 45, 43, 65, 69, 40, 44, which we replicate here. So once we have those cell means, then any kind of contrast we want to do, we can attack. So kind of just exactly what we're having there. So suppose we want to compare the average of the 2 heights equal to the middle cell. So the average, so we want to compare the average of the 2 height in the middle cells with the average of the other 4 cells. So namely, in this case here, we got mu 1, 1, mu 1, 2, mu 2, 2, or 1, 3, mu 2, 1, mu 2, 2, mu 2, 3. So if we look at this thing here, and we go back to our notes, not SAS, we go back to our notes, I'm going to go back up here and grab this. So in this example we're looking at here, we're focused on these 6 cells. So if you remember what the thing just said, we want to look at the average of these two, the middle two. So if we look at the middle, so let me go real quick here. So the fill, put no fill. So we look at the average of those two compared, guess we'll go this way. So in this case here, we'll go no fill. So if we go here, see if I can get this way. See if we can get this just right. So basically we want the average of these two compared to the average of the other 4 cells. So that's the contrast we want to look at. So we want to test the average of the 2 heights in the middle cells with the average of the other 4. So with this approach, this contrast should correspond to the research questions formulated before examining the data. So if we go back to this, so let's go ahead and do this ourselves. So if we go back to SAS, so we want the average of the middle two. So the average of level 2 height. So in this case here, I'm going to grab these middle two that we just did. And like we said, in this case, this average is adding the 2 coordinate-wise and dividing by 2. So adding coordinate-wise and dividing by 2. So that gives us the average of the 2 heights. Let's go ahead and take a look at the estimate to see if that's right on. So we go here back to this. So we get 65, 69. That average is right on to 67. So let's grab the other 4 cells. So I got those ones, level 1. These 2, level 2. And now I can go, okay, let's go ahead and estimate. Move this over just so it hangs out with the other ones. Let's call this average of the rest. So again, add up coordinate-wise, divide how many we got. So in this case here, the intercepts are 1. The height are 0.5, 0, 0.5. So we go to the width. So we go 0.5, 0.5. And then we go, okay, height, star, width. So we got, add them up, divide by 4. Okay, so let's go ahead and see if this works as we start moving forward. So in this case here, the average of the four, 45, 43, 40, and 44. So the average of those guys as we start moving forward with this one ends up being 43 if you average those four numbers. So again, that works well. So now we have these estimates. Grab the ones we just did. So the average of the other two compared to the average of the rest. So again, setting them equal and doing that hypothesis is the same as subtracting one from the other. So I'm going to call this estimate HO, right? So in this case here, we're going to just subtract coordinate-wise. So intercept 1 minus 1, 0. So remember we said anything followed by entirely zeros does not need to be in the estimate statement or the contrast statement. So height, subtract 1 from the other. So this becomes minus 0.5, 1 minus 0.5. So remember, the terms in this add up to 0, so it's truly a contrast. Go to width. When we do this, subtracting coordinate-wise gives you 0, 0. Does that need to be in the equation? Remember we said when something's followed entirely by zeros, doesn't need to be in the equation. If you keep it there, it's no harm, no foul. Again, it's just SAS will realize that that term is not contributing to the model, so it's not something we need to be worried about. So we'll go here to this width. So again, subtracting coordinate-wise, 0 minus 0.25, 0 minus 0.25, 0.5 minus 0, 0.5 minus 0, 0 minus 0.25, 0 minus 0.25. Remember we said we had a legitimate contrast if the sum of all the coefficients for each term summed to 0. That sums to 0. This is 0. Those terms sum to 0. So namely, is there a significant difference between the average of the first of the middle display compared to the average of the rest? Let's go ahead and take a look at the output. So if we go right here, 67 is the average of the middle two, 43 is the average of the rest. That creates a difference of 24, which is highly statistically significantly different than 0. So therefore, the average of the middle display is significantly different and significantly superior to the average of the remaining 4 cells. So that's cool. You know, so the only thing we need to be aware of is we need to get this right. Once we get these cell means, then it's nothing more than adding coordinate-wise. If you're wondering if whether or not these cell means are correct, you lean on the Ellis means that contains the interaction to make sure the cell means are matching your estimates. Then with these estimates to create the contrast, it's getting the respective terms and adding coordinate-wise or subtracting coordinate-wise, whatever you're doing mathematically. That's what we need to think about. So again, we just did that. And for us, the estimate statement did it for us. And remember, in this case, when it's an estimate statement, it can also be written as a contrast. The big thing for us in this case, I think, when we run this out, the contrast does the respective test that we want, but doesn't give us any kind of estimated difference, which we see right there. So again, remember the T is the estimate divided by the standard error. Right? And then this term squared is our respective F that we see is 148.65. The estimate in this case works better because, again, it gives us the direction of the effect, not just the significance. So we can say, yep, there's an on average estimated difference between the respective two combinations corresponding to 24 cases sold on average more for the average of the two middle designs compared to the rest. So again, that's something we just need to keep in mind as we move forward. So again, contrasting the middle two versus all the others, you can see there. So again, we got to keep in mind now, the ordering of the iteration all depends on the class statement. That determines everything. If for some reason we're dealing with something that has a fraction like 1/3, remember the divisor command we had in chapter 17. You may need to use that again as we move forward. So that's what we got there. I'm going to go back to our original code. Not that Word document, our original SAS code. So if we go to the original SAS code, you can see here, so let me just come back fresh. So we're right here, average in the middle, average of the rest, respective contrast that we see there. So again, whether or not you have the intercept in the model or not, line 347 and 348 will give you exactly the same thing. It could be written as an estimate statement if you want. So now, how about this? Let's do the next one. Suppose we wanted to look at the mean for mu21 compared to the average of the remaining three. So now the average of the remaining three, if I pull this up, is nothing more than adding each term coordinate-wise and dividing by 3. Well, now with the dividing by 3, this is where the divisor can come in. So 1 plus 1 plus 1 is 3. I got the divisor 3. The height, 0, 1, 2, divided by 3. The width, 1, 2, divided by 3. And then adding these up coordinate-wise, 0, 0, 0, 1, 1, 1 divided by 3. So now when we want to look at the contrast of mu21 compared to the other three, the big thing we need to do is get mu21 in a common denominator. And then in this case, when we want to do the respective estimate, in this case, it's looking at these two statements, subtracting one from the other to get the respective estimate statement, right? Subtracting one from the other. So in this case here, I'll put the mu21 on top, this one underneath. So subtracting coordinate-wise for this second contrast, 3 minus 3 for the intercept. Don't need the term there since it's followed by 0. So the height, 0 minus 0. 3 minus 1's 2. 0 minus 2's negative 2. Do the same thing with the width. 3 minus 1's 2. 0 minus 2's negative 2. Then the height by width interaction, 0 minus 0. 0 minus 0. 3 minus 0 is that 3. 0 minus 1. 0 minus 1. 0 minus 1. So contrast 2 gave us the respective contrast we needed between, as we said, cell 2, 1. So if we go here with the cell 2, 1, right? So here is, let me get up to the top. Well, a lot of statements here, right? So this ends up becoming cell 2, 1, 65. The average of the next three, 51. That creates this difference of 14. That's in there, which is significant. So that 0.0018 is the same thing we get off this contrast too. So again, keep that in mind as we move forward. So in this case here, we ended up getting, in this case here, the, right, so we end up getting this guy right here as we move forward. So that's our contrast 2. So contrast 3, in this one here, I'm looking at the average sales of the regular. So again, adding them up, dividing by 3. You know, when we divide by 3, we get decimals. That's why the divisor got 3's in the mix. All right, this is the average of the wide. So if we want to focus on the average sales of regular and wide, we compare these by subtracting coordinate-wise down the list. So intercept 3 minus 3, that's 0, that's gone. The height, 1 minus 1, 0. 1 minus 1, 0. 1 minus 1, 0. So that's gone. The width, 3 minus 0, 0 minus 3. And then the height star width interaction. So you got 1 minus 1, 1 minus 1, 1 minus 1 divisor 3. So now, if you guys recall, we had these two rules. If we summed the alpha betas, right? So that's alpha beta 1, 1, alpha beta 2, 1, alpha beta 3, 1. The alpha betas sum. They sum to 0. Similarly with, in this case here, this is alpha beta 1, 2, 2, 2, 3, 2. So they sum to 0 as well. Whether or not you catch those nuances, SAS, your friend on line 383 catches it for you. You know, so again, we don't need to be bogged down on a lot of those rules, since the SAS output will give a lot of that to us as respective information. So again, as you guys could see, on my respective contrast, the two contrast 3s give exactly the same thing. So whether or not you use this one, because it's my fault, you use this one because it's easier to bookkeep, or line 383 because you remember that issue with the alpha betas, it's up to you, right? A lot of times I'll do 382 because it shows all the bookkeeping. It's showing exactly the algorithm and how I'm mentally coding the data to perform the respective correct task. So that becomes really the big issue as we move forward. This one is getting the difference between regular and wide for display low. Again, subtracting coordinate-wise. The difference between regular and wide for the mid-range shelf. And then similarly for between regular and wide for the high shelf. Again, subtracting coordinate-wise. So this is our del 1, del 1, 1, del 1, 2. This is giving us the difference of the deltas. We do the same thing, 1, 3, 1, 1, 1, 3, and then 1, 2, 1, 3. So this is the difference of the delta 1, 2, 1, 3, 2, 3. We said if we want to form a simultaneous contrast in SAS, it's just having our contrast term separated by a comma. So this component here, that's right there. This component here is right there, and this component here is right there. So that is simultaneously testing, in this case here, if we go back to our Word document, this is basically testing this difference compared to that difference, this difference compared to this difference, and then finally this one compared to that one. This is where the money of the ANOVA really is made. This contrast here should match exactly the two-way ANOVA results. Let's go ahead and run this real quick. So when I run this, right, so here is the respective contrast. So that simultaneous contrast gives a p-value of 0.37, which happens to equal the p-value for the interaction. So again, the contrast can really do a lot for us as we start moving forward and start getting after things. If we want confidence intervals for the contrast, remember you need a CL parm in the model statement in SAS. The CL parm coupled with this alpha level will do the respective estimate with confidence intervals. So we need to be aware of that as we start moving on. So one of the things we start seeing is, the sums of squares. When we remove a term for the model, we put the variation associated with that degrees of freedom into the residual. So again, if we start doing parsimonious models, the sums of squares explained for that term will automatically fall to the error. So again, this going to the error is what we call pooling. So one of the big things is we have more degrees of freedom when we ignore terms, but we just got to keep that in mind. So if you look in this one, the SSA, SSB, SSAB is right there. So if we took the interaction out of the model, the sums of squares error would be absorbed, or the sums of squares AB would be absorbed into the sums of squares error, and that will affect the respective test and the respective degrees of freedom of the estimate. So that contrast, we're going to see a lot of them when we're doing it live with respect to a lot of the stuff that's going on as we move forward. So let me do one thing really quick. So now we're at the last topic that we need to do in chapter 19, and this is power. Now, unfortunately, we can't use proc power to do power two-way ANOVA. To do power for the two-way ANOVA, we need to bring in this other proc called proc GLM power as we proceed. So if I take you back to the PowerPoint slides, as we see here, this is giving us a little example. Now, the best way to do power for a two-way ANOVA is to create a data set that contains the cell means for the respective combinations, in this example, of fluid, water EZDZ1, with dosage, low, high, and the respective outcome Y. These are the observed cell means. So if we wanted to do proc power or calculate power here, I would go proc GLM power data fluids. This is the cell means. Class name would be the two factors. Everything here looks like our two-way ANOVA model. This is what differentiates it from the two-way ANOVA model. The power command. Power. Standard deviation. That's my estimated pooled standard deviation, which is estimated by the MSE, the mean squared error. And then here I have my alpha, my total sample size, and the power calculation. If we want to take a look at it further, let's go ahead and take a look at this chapter 19 power program. So if I go here to open chapter 19 power. So here's the example here. So I'm going to load the data with the cell means. Now, some of you guys may read that you could load raw data into proc GLM power, and that's true. But one of the things I found for the ANOVA models that actually calculate the power correctly is to load the cell means into a data set and bring the cell means into the data set, into the data line of proc GLM power. That, coupled with the power command, will give you either the appropriate sample size for the given power, or the power, or the power for a given sample size. Here I load the cell means. From the cell means, I run the two-way ANOVA. So again, this becomes my estimate of the pooled standard deviation, my alpha level, and the desired power. So in this design, right, you notice how the contrast line is commented out. When I run this, SAS is showing me that for a interaction, I would need 172 observations. So in the example we saw, it was 4 cells. So we had 2 levels of dosage, 2 levels of height. So with the 172, that would correspond to having 43 observations per cell. So we need 172 to have 80% power to detect a significant two-way interaction. We need 28 to detect a significant dosage main effect, and 528 total to detect a significant fluid main effect. If we wanted to do a contrast, so in this case here, if we look at the, let me go back to this output. So in this case here, we got the lactic acid, we got the fluid. So for us, we got the fluid to dosage. So we got water, easy DZ1, low, high. So in this case here, we got the low, the high. So in this case, with the class statement, we have fluid dosage. So the dosage low, high iterates within the water. So if we want to do the difference between high dosage, right, if we were looking at estimate statements, now proc power does not have estimate statements, only contrast statements. And in this case here, when we do this, if we were using the so in this case here, if we were looking at this as a typical HLM, or a GLM rather, general linear model, we were building the estimate statements in proc GLM, we would just go do the same thing here. So let me make sure I just type right. You see it's red in line 29 because the estimate statement is not part of GLM power. But if we go here, we go, okay, in this case here, I'm going to call this water low. So if we go here, it'd be intercept 1, be fluid Level 1, 0, it'd be dosage, 1, 0, and then it'd be fluid, star, dosage. So it'd be fluid, star, dosage. So in this case here, dosage iterates within fluid. So it'd be, in this case, it'd be, I'll be, I'm going to do something really quick just to show you guys. I'm going to load this really quick. I think this is an important point to show you guys. The thing with character variables. Let me copy this. This isn't going to run, but I want to show you what happens. So if I loaded this data and ran this in ProcGLM, well, I mean ran, but it didn't show as much. The big thing here is when you have character variables, the ordering of the levels is not by the way they're ordered in the data entry. The ordering of the levels is alphabetical, low to high, E before W, H before L for the dosage. So we have to keep that in mind as we move on. Therefore, when we start looking at what I was just writing with the estimate statement, this actually is, the water level, easy, high, is that guy right there. So again, we go, in this case here, easy, high, easy, low, water, high, water, low. Why'd they get down there? Did the same thing, estimate, easy, low. So it'd be intercept, 1, fluid, we're still at easy, dosage went to high, then fluid, star dosage. So it'd be easy, low, easy, high, water, low, water, high. Do the same thing here. So we go water, high. So we have the intercept, 1, fluid, now we're on water. It's level 2 fluid. Dosage, we're at level 1. And then the fluid, star dosage. So remember, this is easy, high, easy, low. Water, high, water, low. And then if we did the last one, so this would be fluid, easy, water. Dosage, low, high. My fault. High, low. Then fluid, star dosage. We go easy, high, easy, low, water, high, water, low. So that's our 4 cells, and we want to find the difference of the 2 high dosages. It's doing kind of what we did before. Line 370, 38, and 39, rather, we subtract coordinate-wise. Intercept 1, 1 doesn't need to be there in a contrast statement. So line 41 doesn't have the intercept. Fluid 1 minus 0, 1, 0 minus 1, negative 1. The dosage 1 minus 1, 0, 0 minus 0, 0. Anytime a term has all zeros, doesn't need to be there. And then fluid 1 minus 0, 0 minus 0, 0 minus 1, 0 minus 0. So again, remember, the estimate statements don't work in ProcGLM Power, but we could write them to help us lay out a contrast of interest. So when I go here and look at this contrast, proc-GLM power would give me the sample size for 80% power for the main effective fluid, the main effective dosage, the interaction, and then the sample size required for at least 80% power for the contrast. So namely powering the on average difference between easy DZ high and water high. So we need 140 per cell to have that significant contrast. So that's really a lot of, stuff that we start getting into as we start moving forward, right? So we got that right there. So now if I put 100 total, the power would be 658 for the contrast, 570 for the interaction, 57%. If I went here, if I made it 102, run these two back to back real quick. Right, so if you guys see here, I asked for a sample size of 100 in this case, right? So as you guys can see, this would give me the power right there. So keep an eye on these. When I bump the sample size up to 102, right? When I bump the sample size up to 102, when I bump the sample size up to 102, what happens here? With 102, nothing changed. When I ask for a sample size of 102, see, SAS will give me the actual size, 100. The reason I can't use the sample size of 102, in this case, I have 4 cells. So my sample size needs to be some number divisible by 4. So you might say, well, why did SAS drop down to 100 instead of going up to 104? Well, when we're dealing sample sizes, when we say 102, we're telling SAS that is the most sample size I can get, right? It's the most I can get, 102. So assuming 102 is the cap, so in reality you need 100, right? So that's what SAS is saying, realizes you cannot go beyond 102, so it'll drop down to the next cell. If our cell sizes were not equal size, I can include a weight statement in this case. So namely, in this weight statement, my cell sizes are the water lows 5 times bigger than water high, and easy DC low and easy DC high are twice as big as the water high. When I run this, that has my cell means and now the weights for the cell sizes. When I go here, this is the original data for 80% power. So pay attention to the end total. So we saw this already. So it was 172 for the interaction, 140 for the contrast. So now when I go with these weights, the big thing here is line 85 tells proc-GLM power that my cells come with different weights, right? So I'm including those weights into the mix. When I run this with fluids too, you can see real quick here, SAS is going, okay, for the interaction, I need 240. For the contrast, 260. So 240. So if you remember in this case here, our cell sizes were 5. No, our weights were 5, 2, 2, and 1. So I'm going to go back to this Word document. So with weights, right? The 5, 2, 2, 1. So the total for the interaction, as we just saw in SAS, ended up being 240. Right? So in this case here with 240, we see our weights 5 plus 2 plus 2 plus 1 is equal to 10. So 240 divided by 10 gives us 24. So we need 24 units. So the sample size we need ends up being 5 times 24, 2 times 24, 2 times 24, then 1 times 24. So there are the respective sample sizes per cell. And then if you notice, this 120 plus 48 gives us 168 plus another 48 gives us 216 plus 24 gives us the 240 for our total sample size. So that's what we got there if we include the weights. If I go back to the syntax really quick, right? So let me go ahead back to the syntax. Right, so this is the delta for the high dosage. I could have a similar thing for the low dosage. So for the low dosage, it would work the same way, but it'd be line 88. And then namely, the interaction is how the difference in high dosage across fluid compares to the difference in low dosage across fluids. So if we subtract this coordinate-wise, 1 minus 1, 0, -1 minus -1, 0, so the fluid term drops out. But 1 minus 0, 1, 0 minus 1, -1, -1 minus 0 is -1, 0 minus -1 is 1. So line 88, that contrast, the delta of deltas, the difference of differences is our interaction. So line 88 and the effect for the interaction gives us the same thing. The contrast, I made it the interaction. So we end up getting that there. I don't know if we have the Castle data loaded. So let me go ahead and just open up the Castle data real quick. Well, actually, we probably should have it open. It's on this problem. So again, this is our, so as you can see, with the Castle data, I'm using the mean statement and sending that to an output file. So I can use the ODS to create an output file, right? Here is my mean squared error, my root MSE. Here's my cell means. So with my cell means, the ODS put the cell means in a data set. So as you can see, I'm taking this into ProcGL Power, my cell means, my root MSE here, right? My root MSE here. So just run this again real quick. So in this analysis, my root MSE is 3.214550. So when I'm here, I could put the mean, the cell mean data file into the data set, my root MSE, and as you guys can see here, I would need 54 total subjects to have a significant interaction. So remember, this is these are 6 cells. So the 54 divided by the 6 cells means I need 9 observations per cell to yield a significant interaction. If you recall with Castle data set, we only had 2 per cell. So as you can see here is I'm simulating data for the 9 observations per cell with the cell mean, and then this is my standard deviation. So in this case here, I'm simulating data, 54 observations. When I do this, right, you can see my simulated means pretty close for the 1-1 cell, pretty close for the 1-2 cell, pretty close for the 2-1, the 2-2, a little bigger for the 3-1, right on for less than 1 unit for the 3-2. So in my simulated data, does it give me a significant interaction? Yeah, it does. So it looked like if we had 9 observations per cell with that standard deviation, our simulated data gets a little slightly bigger, and the respective cell means, we would have a significant interaction, and our simulation created one that matched that. So that's pretty cool. So that's pretty cool there with respect to chapter 28 or chapter 19. So they were the big components with respect to the two-way ANOVA. So again, if we review what we did in this Word document, we laid out the formation of the model. We laid out the idea of the AFADA approach, the main effects portion of the model, the interaction portion of the model, which is the most important, issues with model building, how to assess HOV. We use the AFADA variable. Then we started going into contrast and estimate statements and multiple comparisons, adjustments there as well, and then how to do power. What we want to do now is to go into chapter 20 real quick in this last portion of this slide. So let me go ahead and get us out of that chapter and get us into chapter 20. And with chapter 20, just to lay this out to you guys before, it's only 9 slides. Another area of the book that I don't agree with, and in this case here, chapter 20 says you have a two-way ANOVA, but we have 1 observation per cell. If you have 1 observation per cell, you're not doing a data analysis. You're just displaying the data either in a graph or descriptively. So namely, we have the same two-way ANOVA, but the most important thing is each cell size is only 1. And that goes again, you can't, if you have 1 observation per cell, how do you know whether or not that observation is not an outlier? We don't, right? So these are things we need to think about as we start moving forward. On D2L, you'll see this reference I have on D2L about needing 7 observations per cell. So again, there really becomes an issue with respect to the 1, and that 7 observations per cell is a rule of thumb, a rule to go by. 1 observation's crazy. Now, the only way to, quote, analyze this data is just to display it, just to display it. Nonetheless, the book starts going, well, hey, some of you guys may be involved in these small-ish beginning studies, and they could actually be called phase 1 studies. So a lot of stuff with the coronavirus, the COVID-19, you heard about these phases of study. Well, a lot of times the phase 1 are the beginning studies for medications or vaccines. So in the way the book attacks this two-way ANOVA model when you have one factor is to focus first on the main effects portion of the model. So for us, it's namely main effect of A, main effect of B. The big thing is, with only one observation per cell, we can't fit the two-way interaction, or else the model's over-parameterized, which obviously is not estimable. So in this case, getting the cell means, everything works business as usual, and this becomes the ANOVA table. So the main effect of A, the main effect of B. And then you get expected mean squares, really the MSEs being estimated by sigma squared. But if we go to this chapter 20, page 882, so let me go ahead and take you to that part of the textbook. So we go to File, Open. I thought we were at that part of the textbook. That's all right. I'll go to STA 513. We'll go to the textbook. We'll go to chapter 20. And I think it was 882. So in this 882, we have analysts in an insurance commissioner office studies premiums for automobile insurance charged by insurance companies in 6 cities. Right, the 6 cities were selected to represent different regions and different size of the city. So we got east, west, and small, medium, large. Here we have one observation per cell. So let me go ahead and open up this data file here. So it's chapter 20, 882 that you guys see right here. So one observation per cell. Let's put a little label on the size that we see. So now if I decided to fit the two-way interaction, size, region. If you guys see this notation with the vertical line, realize that line is the same as this. They're exactly the same line. SAS just interprets this as this, right? So they're exactly the same line. Whether you use the line 30 or line 31, it's up to you. Some people like line 30 because it's more compact, but basically this is just saying the factorial design for those two factors, which means we model the two main effects as well as the interaction. So when we go here, when we fit this model, including the two-way interaction, you guys will see this, right? When we fit the data like this with one observation per cell, we're over-parameterized. We have no degrees of freedom in the error. Anytime we want to do an analysis, we need degrees of freedom in the error. We need that MSE. So without degrees from, without any money in that row, we can't perform an analysis. Every analysis costs money. Our money is really the degrees of freedom in the error. And if we don't have anything, we can't do any analysis. Nonetheless, when we look at the model, we could see it basically estimates the cell means. Again, we look at this two-way ANOVA, look almost kind of like they're running parallel, but maybe not exactly. But to me, with one observation per cell, there's the story. Just show the data, right? You really can't do any analysis on this. But the book will walk you through an analysis. The way they walk through the analysis is they say, hey, let's get the main effects model fitted, or fit, which we got right there. Right, so as you guys could see, in this one, we have a main effect for size and a main effect for region. And that's pretty understandable. You know, the blue's always on top of the red. And we know on average, regardless of region, here's the average for large, medium, and small is obviously on average much smaller than the other ones. So this is giving us a little plot of the mean profile like we just did there. But now, in this case, to the book, in this example of one observation per cell, they say, well, let's fit the interaction through this process we call the Tukey additivity approach. And basically what it is, instead of burning all of our degrees of freedom on categorical levels of the predictor, SAS goes, let's kind of trick the model into doing it. The first step is to get the means for each level of factor A, which is size, which we're doing on line 66. The same is to do the same thing for factor B, right? So again, these are our cell means for small, medium, large. Factor B for, you know, the mean for, in this case here, region 1, region 1, region 1, 190, region 2, region 2, region 2, 160. So with the Tukey additive model, we get the deviations of the mean for level A and the grand mean, the deviations for the mean for level B and the grand mean, and we create the interaction term based on these alpha and betas. So in this case here, I fit this. So with this term, we can fit the interaction model now without the interaction term being a function of the categorical predictors. It basically, in essence, becomes a continuous quantity. So when we do this model with this Tukey additivity term, we can see in this case, instead of the interaction being 2 times 1, 2 degrees of freedom, the Tukey additivity model created a 1 degree of freedom predictor. And therefore, we're able to do the analysis because we have 1 degree of freedom left in the error. Now, so again, the degrees of freedom of the model total is the sample size minus 1. 6 minus 1 is 5, right? We burn 4 degrees of freedom on the model, which leaves us 1 in the error. So anytime we want to do an analysis, we need a degree of freedom in the error. With this Tukey additivity approach, we do not see evidence of a significant interaction between size and region. Again, this is a huge limitation that we only have 1 observation per cell. So you got to really take that, you know, for what it's worth. Again, I said it at the beginning, I'll say it now. You know, to me, when I have this kind of data with 1 observation per cell, there's the story. Right? And this story could be a matter of the investigator saying, these values legitimate? Are these values legitimate? So some of it may be questioning the data. Then some of it's saying, does the data provide any steps, any thoughts about moving forward with continued data analysis or continued data collection? So, I mean, this Tukey additivity approach is fine because namely we're creating this interaction term only using 1 degree of freedom. But again, you know, this lays out the step. We find the overall average, the average per level of factor A, in this case region, the levels per, the mean per level for factor B, which in this case is size. Then we get this alpha effect, which is the deviation of the average per region from the overall average. Same thing for the beta, the difference of the average for the per size for the overall average. And then we calculate the A-B interaction of these continuous quantities. and then fit the model with the main effects region size and this 1 degree of freedom term. And that doesn't burn or use up all of the degrees of freedom. The big thing is, if the interaction is determined to be significant, try to employ various transformations or remove it. That's what the book's saying. I don't agree with it, and I wouldn't even analyze this data with 1 observation per cell. This has huge, not huge power, it's hugely low. It's very low power. So really, this chapter 20, if some of you guys run into this out there in the world, you've seen it, I would not really look at analyzing this data under an analytical model, just really display the data. 1 observation per cell is not real in analyzing. So just keep that in mind as you move forward. And that wraps up chapter 20, which was one of the shorter chapters. And again, this wraps up video 7. So I'll see you guys in video 8 for chapter 22. And I'll talk to you soon. So thank you all.